We are going to continue on our journey with polynomial functions. We're going to be working on how to evaluate them through function notation. We're going to use them to model data. We're going to add and subtract polynomial functions. We're going to find a composition of functions, which is going to also pull from function notation. And we're going to graph basic polynomial functions. So first, let's look at the definition of a polynomial, which you've already seen, but let's revisit it. A polynomial function has a degree of n, where n is the highest exponent and the number of terms presented for the function. So for example, in this example, this polynomial would have a degree of 2 because 2 is the highest exponent. Then they're given the information in what we call function notation. Function notation is pronounced f of x. Typically, that parentheses with a -4 would have an x in it. When we replace that x with a value, the function notation is telling you to do the same thing to the equation. So what find f of -4 means is it wants me to replace x in the equation with -4. Now, this is where the mistake happens. When you replace, you have to use parentheses. So I'm going to have to put that -4 in parentheses. Now you can hop over to the Web 2.0 calculator and you can type this in exactly as it looks right here, and it will give you the final answer. If you do not use parentheses around the -4, then it's not going to give you a correct or accurate answer. So that is really the key component to evaluating a polynomial function, is ensuring you're using parentheses appropriately. Now, to use a polynomial function to model data, when I'm using a polynomial function to model data, I'm basically graphing the polynomial function. To graph functions, we will use desmos.com. So what you will do is you will go to desmos.com, click graph, and you will type this equation in. Even if there's a different letter for the variable, we want to make sure that we're using x when we're in Desmos, because it's not going to recognize a different variable. Then we're going to read through the problem, and it says that this p of x is in millions. So that's going to be important as I look at that graph. We're going to use this function to approximate the number of public schools in 2005, which means we are looking for the x value of 5 because it's a number of years from 2005. There are two ways to do this. You can either plug 5 in for x and get this, or in desmos.com, you can follow the graph until you hit the x value of 5, for which the y value would be approximately 49.03. It's probably easier to plug in the 5, but we will be getting to graphing these in the near future. So just typing it into desmos.com in this lesson will just kind of give you an idea of what things are going to look like. Now, to add and subtract them, we've already done some basic work with that. We've talked about combining like terms. We've talked about identifying which terms are alike and using the coefficients for this. But here, I'm going to show you this in function notation. So in function notation, this is f plus g of x. This is not a product. So the goal here is not to multiply f and g by some value, okay? The goal is that you're just going to add the two functions and that's it. There's no multiplication involved. Same thing on the bottom. We're just subtracting those two functions. It's not multiplication, but that's how we show the f of x. So here's an example where I have an f and a g value, and in part A, it's telling me to add them together. So I'm not multiplying this by x. I'm breaking it out into f of x plus g of x. I'm going to put them in. Now, I'm going to combine my like terms. Because there's addition, I didn't need to distribute any negatives. However, in part B, I have subtraction, which means I'm going to have to distribute this subtraction symbol to every single term. Then I can combine my like terms. So when we're adding and subtracting functions, the place where mistakes are made is when you're not distributing that negative through there. Here's another example. In part A, in the first half, they're wanting me to add the two functions together. So I'm going to simply add them together and combine my like terms. In the second statement, what they're saying is to replace x with -1. There are two ways to do this. You could replace x with -1 in f, replace it in g, and then add them together. Or you could find f plus g like you did here, and then you plug -1 in. Either way would work. And remember, when we plug in, we do that with parentheses, and then our Web 2.0 calculator will correctly calculate the answer. Here's another example, and this is a great one because I have subtraction. So I'm going to subtract the two functions, which means I would have to distribute the negative if I had more than one term in g of x. Then I'm going to combine my like terms. And again, f minus g of 1, I can either take that 1 and plug it into f and plug it into g and then subtract them, or I can plug it into the equation that I already found. And make sure when we plug in, we're doing it with parentheses. Even if it's a positive number, we just want to create a habit, and a positive habit that will always work. The composition of functions is going to build upon that function notation. This is f of g of x. This is not fog. This is not multiplication of multiple terms. This is a composition function. And when we write it, notice how instead of x, I replaced it with g of x. So what this is telling me is for every equation, or every x value in the equation for f, I'm going to replace that x value with an entire equation of g. So we're taking a variable and replacing it with an equation. So let's look at how this works. So find f of g of 3. When I rewrite that with function notation, it says find the f of g of 3. So what I have to do first is evaluate the inside value, which means I need to replace x with 3 in g of x. So I'm going to have 3 squared because g of x is x squared. I'm replacing x with a 3. I know that 3 squared is 9, so now I need to find the f of 9. So what that means is instead of an x in f, I'm going to write a 9. So that's the outside function. And so my final answer is a 5. You have to take this step by step. You need to move slowly through these problems. That way you can acclimate yourself and just take a minute to process. When we do these too quickly, we don't process it in a way that we're 100% sure of what's going on, so we can get confused. So you want to follow exactly like I did, okay? Here's another example. So this time I'm doing the opposite, g of f of 3. So I'm taking g of f of 3. I reversed the order here, and I'm going to get a different answer. So instead of x in the g function, instead of x squared, I want to take my f of 3 value and replace that with x. So first I have to figure out what is f of 3. So I'm going to come over here. F of 3 is 3 minus 4. Replace x with 3, which is going to give me -1. Now I'm going to take that -1 and evaluate it in g of x. I'm going to use parentheses so that I get the correct final answer. A is another great practice one with a number, and B is going to be a little different. So you might need to pause between A and B to process some. So if I have f of g of 2, I rewrite that in the appropriate function notation. I'm going to plug 2 in for x of g of x, which would be instead of x cubed, I have 2 cubed. That would give me the f of 8. I'm not done because I still have to take that 8 and replace x with it in the f equation, which would give me 30. So I get a number. For part B, you're going to get an equation and not a number. And that's what's different. So we're going to follow the same process. We put f of x on the inside. And what this means is instead of writing x cubed, I'm going to write the entire equation of f cubed. So f of x is 3x plus 6. That's what f of x is equal to. Remember, we talked about function notation as a replacement. Instead of x cubed, I'm going to write 3x plus 6 cubed. So it's a replacement of the x value, just like we did with the numbers. We're just replacing that x with the indicated information. So function notation is really just telling you what to replace x with. Now we can graph basic polynomial functions with the help of Desmos.com. When I'm working with my basic polynomial functions, the simplest one is going to be called the identity function because it's just f of x. There's no exponents involved, no coefficients, nothing being added or subtracted. And if you go into Desmos.com, start graphing, and you type in y equals x. Because it's a graphing calculator, we're not going to use the f of x, we're going to make it y. When we actually sketch the graph into technology, we have to put y equals. Another polynomial function that's very common would be x squared. This is called a parabola. All variations of x squared are going to have a U shape, okay? It may be an upward U, it may be a downward U. It could be moved somewhere on the graph, but they're all going to have that U shape. And again, if I want to graph this on Desmos.com, I go to y equals x squared, graph. The cubic function is defined by x cubed, so we're logically naming that one. And it looks like what we have below. And it pairs every number with its cube, so you would want to go to Desmos.com and graph y equals x cubed. And that's going to be the basic idea. So if I go to Desmos here, I'm going to type in y equals negative 2x squared. What this chart does is it's saying if I plug in negative 2 to the equation, I get out negative 8. Because when you're in the math lab, it doesn't allow you to just sketch the curve. You have to have points. And I believe for a parabola, I think it's 3 points. And you have to have that highest point. So you could graph this in Desmos and find these points by clicking on the graph, or you could plug into the function table. You're going to plot your points and connect your dots. And again, the lab is going to require you to have that. Now, how do you know what numbers to pick? Well, it's not really a rule that's hard and fast for the numbers to pick. When you graph them in Desmos.com, you want to pick numbers that are in between this highest point. So that's why negative 2 and 2 were chosen, because the point is in the middle of them. So it doesn't matter what values you choose, as long as you're looking at Desmos to get a feel for, I need to have that highest point, and I need to have at least 2 points on either side of it.